All right, pre-calc students, we are going to be going through our 2-5 notes. My name is Mrs. Holmquist, for some of you that are watching this that don't have me right now. And so we are starting this next section. I know some of you haven't taken your 2-1 to 2-4 test yet. This actually isn't a bad thing to do beforehand because we are going to be doing some more synthetic division. And it's actually a little more complicated synthetic division, so it will be even easier when you take your actual test in class or on distance learning. Okay. So on your guided notes here, you can see that there is some typed theorems on here. Sorry, I wrote on mine on accident. So let's talk through what these are and what they say. So your first one's called your fundamental theorem of algebra. Not that you have to have that memorized, but that is what it's called. And here's what it says, is that if you have a polynomial of degree n, it has to have n complex zeros. Some are going to be real, some are going to be imaginary, and then like you saw with the multiplicity, you might have some that are repeated along the way. So we're really going to be combining stuff back from pre-calc A with the complex and imaginary numbers, and what we were just doing in like in 2.4, that found zeros of these higher powered degrees, so a cubic, a quartic, stuff like that. Okay. The second theorem that we're going to be drawing upon as we do this is that a polynomial of degree n is going to have n linear factors. Sorry for the weird space there. And then all of those factors can be written in this form x minus k, all the way up to that n power. And then where a here is our leading coefficient. Right. Now, from the first one, we said some of those, zeros might be imaginary. So some of these k's are going to be complex or imaginary numbers that are going to show up in there. So that's kind of where we're headed. Okay. Key ideas that are going to show up here is that it's called the complex conjugate zeros. And what this says is that if a plus bi is a 0, then a minus bi is a 0. And remember that a plus bi, a minus bi, those are conjugates. That is what the definition of a conjugate is, that we take the imaginary portion and we switch the symbol on it. So an example of this would be if I tell you 1 plus 3i is a 0, tell me another 0, you'd say, well, 1 minus 3i is also a 0. Okay. And then our last one is that if we have an odd degree, so if you're a cubic, a 5th power, 7th power, that you have to have, oops, that was supposed to be yellow, at least one real 0. And if you remember back to kind of that 2-3 section, we talked about it a couple times, but if you have a cubic or anything higher odd power, your end behavior has to end opposite. So it's either going to be like that or like this, which means one's going up, one's going down, and so you must be crossing your x-axis at least once, so you have to have one real 0. Because this graph is all real numbers. This 1 plus 3i that I have written here, that's not graphed anywhere in here. It comes into play in the equation, but it doesn't show up on an xy plane because xy plane are real numbers are on that picture. All right, so let's look at what we're going to do and how this all kind of plays together now. So we want to start working with these complex numbers and review those, and then we want to combine this process of synthetic division. So we can do synthetic division with a 0 that is complex. So this 1 minus 2i is going to be a 0. Okay, so let's repeat our synthetic division process. We are adding, so I put a plus there. It starts off by dropping your leading coefficient. And then remember, I called it like the diagonal. You multiply your diagonal. Now this is going to be a little weird because I have to do 4 times 1 minus 2i, which means I have to distribute it. I'm going to kind of write at an angle so it doesn't get all mixed in there. So this would be 4 minus 8i would be your next part. All right, when we add, we have to combine like terms. So 0 and 8i are not like terms because the 0 does not have the i, the imaginary. And so I'm just going to be adding 0 and 4, and I get 4 minus 8i. Okay, now it's kind of weird. You're like, wait, there's a complex number coefficient, and there is for right now. Okay, then we go and we multiply the diagonal. And so now you're looking and you're like, well, I've got a complex number times a complex number. So back from pre-calc A, we got to look back and go, how do I do that? So if I write them next to each other here, 4 minus 8i. Remember that to multiply these, we have to FOIL. So I'm going to FOIL out here. I'm going to do one with you. I'm going to have you, kind of try some of these on your own as well, but we'll do this one together here. So 1 times 4 is 4. 1 times negative 8i. Negative 2i times 4 would be negative 8i again. And then a negative times a negative will be positive. 2 times 8 is 16. And then I times I is I squared. Okay, another throwback is, okay, well, what do I do with this I squared? Well, I squared is really negative 1. So this n term is really a negative 16. And so I would get, oops, I made a mistake here. 1 times 4 is 4. I was like, sorry about that. Yeah. All right, so negative 12, let's try that. Minus 16i is what those two things multiply to. So this is negative 12 minus 16i. Make sure you give yourself room on your paper. It's hard to do it on here too. All right, so combining these, again, the 17 and the 12, or negative 12, are the real terms. So those are going to go together. And I'm going to get 5 minus 16i. And then I would do this again, because I need to do this 1 minus 2i times this. And so what I'd like you to do is pause the video and try this. And when you feel like you are ready, go ahead and hit play and then see if you got what I got. All right, so I ended up getting the negative 27 minus 26i. And you can see my work there if you need to check something. Minus 26i, there we go. Putting those together then, again, it's still the real parts go together. So I'd have negative 13 minus 26i. Okay. And then we got to do one last one, and you're not going to get tons of these. I know you're thinking this is a lot of work. It is a little bit at the beginning here, but you're not going to get a ton of these on a homework assignment. So negative 13 minus 26i. So let's pause the video and try that again. All right, so when you do this, you should get, so negative 13 minus 26i. I would get plus 26i, and then I would have plus, let's see, 54i squared. Oh, I'm sorry, 52. Okay, and then putting those together, this is really a minus, sorry, that's 52, minus 52. So then overall I have minus 65 because those would add out. And then negative 13 minus 52 is then negative 65. So negative 65, which I did tell you that was a 0. So that's good that we got a remainder of 0. That means we did our algebra correctly along the way. Okay. Now, the one thing that from the first page we talked about the complex conjugate zeros, and that if a minus bi is 1, then a plus bi is. Well, in this case, since 1 minus 2i is 1 plus 2i is also going to be a 0. And in order to get these leading, so these coefficients are complex numbers, what's going to happen is when I do synthetic division with my complex conjugate, or my conjugate, we're gonna end up with all real coefficients down here. So I'll show you how that works. So I drop my 4, I multiply, and I have 4 plus 8i. Okay, when I add down, the 8 i's cancel, and then I have 8 here. Okay, multiply again, so I'd have 8 plus 16i. Again, your i's cancel, and you're left with 13. 13 then would be 13 plus 26i, and there is your remainder of 0. Okay. Now, what you just created, or what you just did, you started with, so in this first line, this would be a 4th power, so you have your power 4, your cubic, your quadratic, your linear, your constant. And so this end here is now a quadratic. So 4x squared plus 8x plus 13, that's what the last line is. These then are those complex zeros, and all of those can be written as factors as x minus k. That was one of the things we talked about earlier. So I'll have x minus, and then my first is 0. Be careful with parentheses. Your k has 2 pieces, so you do need parentheses. and then minus 1 plus 2i. We don't need you to distribute that negative or simplify. We can clearly see like this is your k, and we are perfectly happy if you leave it just like that. Okay. So some great algebra coming back in here with the foiling and what is I squared equaling. And then the nice part is you'll know if you do these right, because they're gonna, if it tells you it's a factor or a zero, you have to get zeros as a remainder. And after you do synthetic division with a complex number and its conjugate, you will end up with all real leading, or not leading coefficients, just coefficients, all real coefficients for, you know, whatever your, in this case, quadratic was my ending. Okay, all right. Oops, I'm sorry, there was an example on the bottom of that page. Slide down, there we go. All right, let's practice foiling again, just because that is going to be one of the bigger parts for today that we talk about. And so I want to foil these things together, and a recommendation to make things 10 times easier is multiply or distribute or foil your complex, I'll say factors first. If you go in order, you are going to get these huge things, and eventually it will get down to be something with all real coefficients, but it will take a while until you get there, and it will get a little bit out of control. So instead, here's the first, you know, factor and the second complex factor. Put those two together first. And so I am going to distribute this negative so that I don't have double parentheses. So minus 1 minus 2i. And then this one is x minus 1 plus 2i. So I'm going to FOIL these two together first. I'm going to put the x plus 2 here just so that I don't lose track of it. So if I distribute my x to everything, I'd have x squared minus x plus 2xi. Okay, distribute my negative 1, so negative x plus 1 minus 2i. Okay, now I'm distributing my negative 2i here. So negative 2xi positive 2i, and then this would be minus 4i squared for my next part. All right, let's go through and kind of do some matching here. I got a positive and I've got a negative 2xi, so those are going to add out. I've got a minus 2i and a plus 2i, so those cancel out. Remember, I squared is really negative 1, so negative 4 times negative 1, this should become a positive 4. So collecting like terms here, I have x squared. I'm going to use a different color here. So I've got an x, or a negative x, another negative x, so minus 2x. And then I've got a 1 and a 4, so I've got plus 5 for my next part there. And just like I told you, synthetic division, when you do it with a complex and its conjugate, you get real leading or coefficients. It's the same thing. When you FOIL together two conjugates, yes, they're with the x as well because they're in the a factor format, but you will get positive leading coefficients. So there should be no i's left once you have multiplied those together. And that's why we tell you to do them first, because if you do these two first, you know, the first and the second one, you're going to get i's everywhere. And then more i's come in when you distribute with that one, and it gets hard to keep track of all of the terms. Okay, and so we do need to take that last step to multiply them. So I'd have x cubed minus 2x squared plus 5x, distribute the 2, so 2x squared minus 4x plus 10, and then putting that all together, I've got x cubed plus x plus 10. Is what those three things FOILed together gives you. All right, now to your next examples. Write a polynomial in standard form with the following zeros. And so you can see we've got this multiplicity idea coming back. This one's got a multiplicity of 1, but still. And so when I have negative 2 as a 0, your zeros all go in the form x minus k, back from one of the theorems on that front page. And so this negative 2 is really x plus 2. You can also think you're putting it in inside opposite. So you're putting the negative goes plus 2. Now that multiplicity of 2 means there are 2 of them. And so because it wants me to write it in standard form, I'm going to write it as another one because I know I'm going to have to multiply out. So standard form basically means there's no parentheses. So everything's going to have to be multiplied out. Okay, my second 0 is that 4i, so I'm going to have x minus 4i as well. Now, here's the key thing to remember. Write yourself a giant star reminder. I'm going to say remember the conjugate. Okay, if you FOIL these all together, you are going to get a very gross looking answer because there is another 0. No, it's not listed, but it comes from that complex conjugate 0 theorem, that if 4i is a 0, then negative 4i is also a 0. And so you have to remember this part. That's why, highlight, circle, star, whatever you got to do. And you, again, can recognize that something's going wrong because your answers are going to be, in this case, a quadratic, or I'm sorry, a quartic. And you should have no i's in your final polynomials because it says it's a polynomial. There are no complex coefficients in a polynomial. They're all real. So if you forget this, that will be your tip off of, oh, a polynomial can have i's in it, and you have i's all over the place. Okay. Now, just like the last one, put these two together first. I'll write FOIL here, so that you don't. I'm going to put both pairs together just to make your life a lot easier and just get rid of the i's right away, basically. So these two multiplying, I'm going to have x squared plus 4x plus 4. So when you FOIL out and combine, these ones I'll actually write everything out here. So x squared, I'd have plus 4xi when I distribute the x. Okay, then minus 4xi, and the last would be a negative 16i squared. Okay, so putting that together, I'm going to leave this one the way it is, and then my last one, this would be x squared. This would really be a plus 16 then, because you have times the negative 1, so plus 16. Do one last distribute and combine like terms. So x to the 4th plus 16x squared plus 4x cubed plus 64x, 4x squared, and then plus 64. Okay, so final x to the 4th, where's my cubic? Plus, there it is, 4x cubed plus 20x squared, and then I've got my 64x and my 64. So I'm going to put a y equals because it said write the polynomial. So there's your equation of the polynomial that has those 4 zeros. All right, question 2. State how many complex and real zeros this function has. All right, this is going to be a calculator question. So you will be able to have a calculator and look at it and say, all right, how many, well, for part of it, I should say. So first of all, when I ask how many complex, this is actually, oops, I forgot the E. This is actually a very, very easy answer, because if I go back to this, that if you have a degree n, you have n complex zeros. So whatever your degree is, that's how many complex zeros you have. Oops, sorry, bottom here. And so when I look at this and I look for my degree is 4, because that's the highest power and there's nothing multiplying. So you have 4 complex zeros. So I'm just going to write that. This is the degree. That's where that number came from. So that I would expect without a calculator. The real portion, though, you're going to get that number by looking at your graph and seeing how many x-intercepts there are. So int is my intercepts shortcut there. And so if you were to type in this one, you will see that it crosses the x-axis twice. So how many, x-intercepts, like I said, same with x-intercepts. Another way to say it is your zeros. Another way to say it real, these are now real, is x how many times it crosses your x-axis. That's right. Cross x-axis. Okay. So I will say, make sure you can do this part without a calculator, which is just the degree. All right, we're almost there. So let's put this all together. So 2.4 and 2.5 are really going to come together right here and merge into one approach. This will not be on, obviously, the 2.1 to 2.4 test in terms of what kind of solutions you're getting. The process is, though, because we are going to be finding all of the zeros and writing linear factorizations, which is basically what we were doing in 2.4. The only difference is you can get some now that are complex zeros, so meaning they have imaginary numbers. Okay, it is going to start the same though. You are going to graph this thing, and you are going to look for, I'll say, candidates for synthetic division. There we go. So again, what that means is, where does it look like it crosses your x-axis? Where does it look like there is a rational zero? That was the 2.4. That, remember, we called it, we cheated off your calculator because we have them. So let's use the technology. But back in the day, they were not able to cheat off the calculator, and they had to do it by trial and error. Okay, so if we type this in, and again, I'm going to assume you guys can all graph at this point, -2. It looks like it crosses that. So let's check and see if it is by doing, I'll put step 2 here, synthetic division. Okay, you have to go through the synthetic division process. You cannot get those numbers and just write your answer off your calculator, especially now, because you won't get all 4 zeros, because we're going to have 4, because that's our degree. All right, so let's do our synthetic division. So I take my coefficients, 1, 1, 7, 9, and -18. I probably wrote those too close, but it's okay. All right, drop the 1, multiply for -2, add to -1, multiply to 2, add to 9, multiply to -18, add to -9. Those multiply to +18, which then gives us my remainder of 0. So you got a good candidate off your, I spelled the word candidate wrong. Okay. You got a good candidate off your calculator. Now, because we had a 4th power, this last line is now a cubic. Well, I still can't get to a complex if I have a cubic, so I need to go to my calculator again and go, all right, I need another rational 0. Well, 1 looks like a good candidate, so let's try 1. All right, pause the video, see if you can do the synthetic division. You should get a remainder of 0. So try synthetic division on this one. When you're ready, hit play and watch the solution. Okay, welcome back, those of you that actually hit pause. So drop the 1, multiply, so you get 1 here, add those for 0. 1 times 0 is 0. For those, add to 9, 9, and then there is your 0. So right now, what you have, I'm going to rewrite f of x. So it started as a 4th power, still is a 4th power, but now I have x plus 2, x minus 1. Okay, these are what we call our linear factors. What's left on my last line there is x squared plus 9. Okay, and this thing we are going to call a, I'm going to slide up so I can write it better. This is called an irreducible quadratic. And what that means is that this thing has complex zeros. Okay, and here's how those complex zeros come about. If I set x squared plus 9 equal to 0 and I solve, so I'm going to add 9, I'm sorry, I'm going to subtract 9, and I go to square root, well, that wouldn't have happened in 2.4, but now because we're looking at complex answers, this can, and what I would get is plus or minus 3i. Don't forget your plus or minus. Remember, they have to pair up. All complex zeros pair up, so you need 2 of them. And so if we kind of draw a conclusion here, I'm going to list it on the side here. So your zeros were -2, 1, 3i, and negative 3i. Okay, if we want the linear factorization, sorry, I just sounded out for myself there. So we already had the first two, x minus 1, and now our new ones are our other k values are 3i and negative 3i. So x minus 3i and x plus 3i. Okay, these ones end the same as in 2-4, that you're going to extract the root. That's what this process is called. Or you might need to use your quadratic formula to get your other complex zeros. So just to highlight a couple terms here, you're going to see the phrase, I want a highlighter actually, irreducible. So it'll say write as linear factors and an irreducible quadratic. Then you can stop here. If it asks for a linear factorization, you have to go for another step of solving your quadratic, getting those complex zeros that we found right here, and then writing each one as in that form, x minus k, etc. for all, in this case, 4 of them. All right, I would love for you to actually pause the video when I'm done here and try this one. And you can see the directions as a product of a linear and an irreducible quadratic factor. So you don't have to keep going and get the complex zeros. So see if you can do exactly like we did in the last one. Graph it, look for a nice zero. I'm going to tell you there's one that you're going to use, and it is, it's not a whole number. It's a rational number, but it's not a whole number. So see if you can do synthetic, so find and do synthetic division with the rational number, and then I'll walk you through the last part there. So go ahead and hit pause and try that. Okay, when you graphed it, hopefully you graphed it, 2/3 is actually your number that is a rational zero. It's not great because I know it's a, it's kind of a decimal with that 0.66666, but we can write it as 2/3. So when I put my coefficients here, -2, 6, -4, -24, 16, and I start that process when I drop my 3. Luckily, 2/3 times 3 is 2. Okay, those add to 0. Well, that's nice. 2/3 times 0 is 0. So this is 6. 6 times 2/3, well, I would do 2 times 6, which is 12. 12 divided by 3 is 4. So I get another 0, which is nice. Add to -24, excuse me. And then 2/3 of -24 is -16. And then there is my 0 at the end. Okay. All right, where we are right now, I'd have x minus 2/3. That's what you just factored out. Synthetic division does. And so what I have left is 3x to the 4th plus 6x. Now I don't have a cubic, so this is going to be my quadratic. And then minus 24. Okay. Now, you have a 4th power, and nothing else is like, I should do synthetic division with that. So, what we can, this actually can be factored. Let's put it that way. Notice they're all divisible by 3, so I can factor a 3 out. And I'm going to put that 3 right in front because that's my leading coefficient. Plus, this would be a 2x squared and minus 8. I can factor this again, believe it or not. So this, yes, it's a 4th, but the middle term's a squared. And so here, I'm going to go sideways here. So I have 3x minus 2/3. So instead of starting with x in both of my normal factoring, I can start with x squared. And then I'm looking for what multiplies to 8, -8, and adds to 2, and that would be -4 and +2. This piece then factors again because that's that difference of perfect squares. So I have 3x minus 2/3, x plus 2, x minus 2, and then this x squared plus 2, that is your irreducible quad. Those are R's that look like an M because I attached them. But that's your irreducible quadratic, because when you set that thing equal to 0, you would get the square root of -2, which is not going to be that's going to be your complex answer. Okay. All right, this assignment's going to take a little bit of algebra. It's going to take a little bit of paper because you're not going to be able to fit, you know, synthetic division and all of this stuff in one line. You're going to need to spread it out a little bit. When you're doing something like this, yes, you're going to have to do a couple foiling. Go on the margin, go right next to it. It is good practice with your complex numbers, and it's great practice for just algebra and making sure that you are keeping up on that skill. All right, your 2-5 assignment is listed there on the bottom. It's in Canvas as well. Come with questions, you know, mark things. We're going to do some practice when we come back to class together, whether in person or online. But we'll continue to practice these and give you opportunities, but then you got to let us know what you need help with. So thanks for watching, and have a wonderful rest of your day.